Hello, everybody. So we're coming back here, looking at some more kinetics. We are on page 12, the AP Chem Kinetics outline, and we're going to be talking a lot about energy in this lecture. Now, I want to draw your attention back to something that we call the ice cream graph. One of the most fundamental ideas, actually, in talking about how atoms behave. Up here on the y-axis, we're going to plot the number of molecules, although we could be talking about other particles too. We'll stick to molecules. And the distribution of their speeds. Now, we're basically going to see two curves the way I'm drawing this. One that looks like that, and then one that looks much more spread out like this. Now, at a constant temperature, so to speak, okay, the distribution of speeds for particles would show that, on average, the heavy particles move slower than the light particles do. Okay? The heavier the molecule is, the slower it's going to move. Now, we talked about this a lot back in chapter 5. Okay, go back and review all that stuff from gases. Okay, so what we have to say is that this represents an average. The majority of the particles on this blue curve have this speed. Okay, but some are very low and some are very high. The majority of the particles under the red curve, the lighter molecules, have this average speed, but some are very low and some are very high. What this is showing is that on average, the lighter ones are going to be moving faster than the heavy ones. All right? And that's going to come into play a lot when we are talking about effective molecular collisions. So what's a catalyst? A substance that changes the reaction rate but is not used, or maybe we prefer the word consumed, in the reaction. Now, catalyst, as we're saying that there is a noun, the verb version would be catalysis, which would be a process. Now, how does a catalyst work? Typically what we would say on an energy profile, that time here, actually we'll do an exothermic one. Okay, that's what the energy profile looks like most of the time. A catalyst can provide a lower or even a higher energy pathway for this to happen. If it's a lower energy pathway, more of the particles that we're referring to will have the necessary activation energy for the reaction to happen. If it's a higher energy pathway, then fewer of them are going to have it. Okay? So, let's say it provides an alternate energy pathway. Okay. Promoters versus inhibitors. Promoters lower the activation energy. Inhibitors raise it. So a promoter is going to make the reaction go faster. An inhibitor is going to make it go slower. Now, they can be heterogeneous or homogeneous. If they're heterogeneous, they're in a different phase. If they're homogeneous, they're in the same phase. All right. So, let's try and tie a bunch of this together right now, looking at a reaction, but running it at two different temperatures. So, number of molecules, time. Now, I'm going to draw this first graph in blue again, okay? Then I'm going to draw the second one in red, and I'm going to arbitrarily place a line right there. We're going to call that the activation energy, okay? So, I'm sorry, I didn't mean to put time down here, I meant to put temp. Okay, so what's going on is that this T2 is higher, T1 is lower, and it shows that at two different temperatures with the same reaction, the one happening at the higher temperature, a greater number of those particles will have the activation energy that is necessary for this to happen. Okay? That will be the ones to the right of this line. Okay? And really, I should label this speed. It would be best if we called this speed for this version of the graph. A lot of different versions of it. Okay? So if T2 is greater than T1, more of the particles at T2 will have the activation energy necessary to produce a reaction. Fewer particles at T1 will. Now, will some of them at T1 do it? Yes, but more will do it at T2, which is the higher temperature. When they're moving faster, they're going to collide more often, colliding with each other, not the walls of the container, and they are going to hit with more energy, which gets you closer to the activation energy necessary for the reaction to happen. Now, what I can't tell you here is which particles. I can just say more of them. There's no way to identify a specific particle and say this one will react or this one won't, just based on it being a particle that's there. Okay. Now, the collision model basically says, for a reaction to happen, they have to hit, hard enough and with the right orientation. Talked about this a lot in honors. Okay? So, what are these 6 factors or 6 things we can talk about that'll change? How often they hit, if they're hitting hard enough, and with the right orientation. Well, temperature, concentration, catalysts. That's really the only one that changes the orientation part. Surface area, agitation, you'd probably refer to that as mixing, and the nature of the reactants. Let's get that one out of the way. Some things react and some things don't. Live with it. I don't care what you do to helium. You're not going to make it react. It won't go faster. Pretty much done deal. Now, temperature. If you heat them up, they collide more often. They collide with greater energy. Concentration. If you have more of them there, there's going to be more collisions. Surface area. Greater surface area, more chance of collisions. Mixing them. Basically the same thing as temperature. So these are all pretty similar to each other. Now the catalysts provide that lower energy pathway. Okay? So that really can help us out with the right orientation, but it also plays into this in addition. Okay, so this relationship with temperature was mapped out by a guy named Svante Arrhenius. Now, he basically invented physical chemistry, okay, especially kinetic stuff like that. And what he found was that if you plot the ln of the rate constant, K, versus 1 over the temperature, you get a straight line that goes down. So, the ln of K equals negative EA over R times 1 over T plus the natural logarithm of a constant. Now, K is the rate constant. EA is the activation energy. R is the gas constant. We like 8.31 joules per mole K. And the ln of A is called the frequency factor. We don't really deal with it too much. So, the Arrhenius equation itself can be a two-point form of this equation, where the ln of K2 over K1 equals E sub A over R times 1 over T1 minus 1 over T2. So if I can measure rate constants at two temperatures, I can determine the activation energy from the slope of this line. Or if I know the activation energy, I can find what the rate constant might be at a different temperature. Okay? This is a vitally important equation for the Chem Olympiad, and on the AP Chem exam, you really won't be solving for it mathematically, you'll be talking about it graphically. Okay, so how does this work? We want to determine the activation energy of a reaction whose rate constant is this at 25 and this at 67 degrees. Okay, so we'll call this K1, T1, K2, T2. So if I rearrange the ln of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2, EA is going to equal the ln of K2 over K1 times R 1 over T1 minus 1 over T2. So I have the ln of 9.30 times 10 to the negative fifth per second over 5.54 times 10 to the negative third per second. Seconds cancel. Taking a logarithm of the units kind of pointless anyways. Now R, I'm going to put 8.31 times 10 to the negative third kilojoules per mole K. And I'm doing it in kilojoules just for the convenience. Okay, that's the only reason that the times 10 to the negative third pops in. Over 1 over 298K minus 1 over 340K. The kelvins end up canceling. And this comes out to be about 103 kilojoules per mole when you run that through your calculator. So pretty straightforward solve for the EA. Now, very different question. How much faster would a reaction happen at 25 than at 0 if the activation energy is given? What this is actually asking is for the ratio ln K2 over K1. Remember, rate constants are a proportionality constant that basically tell us how fast a reaction is. So this ratio will tell us how much faster the reaction is at T2. And that equals EA over R 1 over T1 minus 1 over T2, which equals 65 kilojoules per mole. All right. Divided by R, 8.31 times 10 to the negative third kilojoules per mole K times 1 over 273K minus 1 over 298K. The kelvins cancel, the kilojoules and the moles cancel. So this ratio equals 2.40. So if the ln of K2 over K1 equals 2.40, K2 over K1 equals e to the 2.40, which equals about 11. So it's about 11 times faster. Okay? All right. So now, to actually solve for a K requires us to use a little bit of our knowledge of logarithms. In this reaction, we have a rate constant at this temperature. Calculate the value at a different temperature. Activation energy is given. So what we have is the ln of K2 over 2.00 times 10 to the negative fifth, okay, equals, and I have 8.50 kilojoules per mole, okay, divided by R, which is 8.31, times 10 to the negative third kilojoules per mole K, times 1 over 298K minus 1 over 323K. Kilojoules, moles, and Kelvin all cancel out. So, remember that the ln of A over B equals the ln of A minus the ln of B. So the ln of K2 minus the ln of 2.00 times 10 to the negative fifth equals 2.657, which is all of that run through a calculator. So the ln of K2 minus 10.82 equals 2.657, or the ln of K2 equals, and then we move that over to the other side, move stuff around, ln of K2 equals negative 8.163. That's actually a negative, sorry. So K2 equals 2.85 times 10 to the negative fourth. And they told me the unit was per molar per second, which is the same as saying liter over mole second. Okay, there you go. That's the last pages of the kinetics outline. Hope you all are having a good day. This is Morgan signing off.